Okay, it should be good now. Sorry about that.
Okay, it should be good now. Yeah, I confirm it's good.
Okay.
Perfect. Okay, so sorry about that. Now everything is set. So Matthias, you were talking.
Yeah, I wanted to ask Shahar about what do you, as the co-inventor of Cairo, what do you think about the evolution? Do you like it? Do you like the way things have gone? And could you have predicted that things would have gone this way? Yeah, that's just a very large question, I know, but curious about your sentiment on this. Yeah.
All right. Well, Cairo is multiple things. So I'll start with the underlying ZK system. Yeah, at first we made Cairo so that we can create stuff more easily that use ZK proof system, and it was a first of all very cool, and it was a success. We could write complex logic instead of writing circuits by hand. So it was very nice. And then we thought about opening it to the rest of the world. We didn't think at the beginning that it will catch on as well as it did, but a lot of people liked it and tried to use it. Even though Cairo Zero was hard to use, a lot of people were fascinated by the idea of just writing programs and make them ZK proofs. So this was nice. A lot of people wrote a lot of cool stuff. Kakarot is one of them. It's a really impressive project, big project that is written in Cairo. We then shifted to the notion that, okay, a lot of people are writing in Cairo. Let's make it a lot easier. Make a modern programming language on top of it. This is the modern Cairo high-level language, and I didn't say Cairo 1. It's not called Cairo 1. Yeah, I think this was a very, very, very great success. Very good decision that we made to make this program. Programming in Cairo today is really nice, really fun, in my opinion, at least. And I think it's responsible to a lot of the growth we have today in StarkNet. The fact that the Cairo language is very nice and it's safe. And also one of the main benefits, I think, that is that everyone that is working on StarkNet is actually targeting Sierra and not directly Cairo, which means we can change the underlying VM later in StarkNet to make things more efficient as we have more progress and not just be fixed on one thing. So it means that people will seamlessly continue developing on StarkNet, but the underlying VM might change and they won't even notice, just that everything will be a lot cheaper. So that's where I see us going. There are a lot of features I would like to still have in Cairo. If you want to contribute, I encourage you. Yeah. That's
Yes,
about it.
yeah, definitely. That resonates a lot with what Moody said last time, that he started with Cairo, so not with Cairo, not Cairo 1. And yeah, he really liked it. He didn't pick up before because Cairo 0 was just, not good for him. But really quickly, he managed to pick up Cairo and build Ekubo in like 2 months, which is like impressive. It's like a huge code base as well. So yeah, I think let's do you guys have any other questions before we start diving right into the code?
So the first thing I think is Elias should be talking like for 1 minute about the current state of Kakarot and the code base in Cairo 0, because like we're currently doing the transition to Cairo, not 1, just Cairo. But like there is already a huge code base that is written in Cairo 0, and like we have some people that actually still like to write Cairo 0. So we still think, some people still think it's actually a great language, especially because you actually have more management about what you're actually doing and how you manage the memory and stuff like this. So yeah, Elias will introduce the Cairo 0.
Okay,
So okay, so you should mute. All good, all good. My bad. I had the stream open, so there was an echo, but it should be good now. So for context, we started Kakarot in October 2022, so it's been almost a year now. And I would say, like, for this whole time, we developed in Cairo 0, and we're starting to notice the difference in approaches for the two languages. But for context, as I was saying, we have like 100% of code, most precompiles, and we're currently implementing the official Ethereum test suite for the Kakarot Cairo 0 repo. And parallelly, we're working on the migration to the modern Cairo. And yeah, I think that's it. So Eni is currently leading that effort. I'm joining as well a bit. Clément is still debugging and finding new fixes on the Cairo 0 code base. I know Clément is a fan of Cairo 0. He has mastered all the footnotes that Cairo enables him to do. But
that's a good question for you, Shahar. Do you see like any future about with Cairo 0? Do you see something? Is that something that you want to see totally disappear, or are you happy to see people still doing Cairo 0, or yeah, is that like a creation of the past that you don't want people to talk about?
I think there are use cases right now for Cairo 0. I really hope that we can answer them all in Cairo with maybe unsafe code blocks and things like that. Let the people have management when they're not on Starknet and they don't need the safety. Just make it a program for the Cairo VM using unsafe code. Yeah, so once we have that, I don't see Cairo 0 existing anymore, but until then, it does. And it has like a lot of uses.
Yeah, I think it makes sense. Just like in Solidity, you can write URL blocks within Solidity. Yeah, that would totally make sense in Cairo as well. Okay, Eni, if you want to, I think we can start with the code. So if you want to do maybe an overview of the repo, yeah.
Okay, yeah, sure. So first of all, I would like to thank all the contributors to the current state of the Cairo 1 repository. So we have the Kakarot core team, but we also have a lot of external contributors that helped us implement upcodes, helped us refactor some stuff, and help us implement tests for the current state of the Cairo 1 migration. So this is great, and thank you to everyone. And I think the first thing we can do is actually start by looking at some design documents. Because the road to the Cairo 1 migration has not been very easy, and we had to make design trade-offs due like adapting our code to like the new way of thinking with Cairo 1 and eventual bugs that we encountered. So we have some documents. I think it's great if we can present them first. So like that first document we have is about how we, is how we designed what we call the Kakarot machine. So the EVM is a stack-based computer, and that means we're going to use a stacked data structure, and we're also going to use a memory data structure that simulates EVM volatile memory. But during the implementation, we actually encountered some bugs with the way we wanted to implement the design of Kakarot, which required us to find another way to implement our data structures, which is a bit unconventional, but that's a good workaround that we have found to be satisfying. So let me first present this very simple diagram about the architecture of Kakarot's EVM. So at the top level, we have what we call the machine. The machine is composed by the stack and the memory. We have one single data structure for the stack and the memory, even though in the EVM, each execution context, for example, when you start and make a call to an external contract, it spawns a new execution context, which has an empty stack and an empty memory. But due to some limitations of Cairo for now, we had to find a workaround and define these data structures at the top level. So I will we'll dive a bit deeper into the implementation of the structures, but for now, know that the stack and memory are top level. And then we have what we call the execution context, which is all the variables that are specifically related to the execution of a call or anything like this. So once this is in mind,
just quickly explain why we had to do this.
Yeah.
It should be good. Oh no. Okay.
Good?
Yes, all good.
Okay, all good. So I was saying we extracted the dict-based data structures to be at the top level so that we could actually pack a struct, like our self-referring structs, without dictionaries. And that's why the design is a bit odd and not the one we had specifically in mind at the beginning, but after talking with Ori from the compiler team, this is a good trade-off that we agreed on. All right, but how exactly can we simulate having multiple stacks inside one single stack? So first, before looking at the code, just a bit of context, the EVM stack has a maximum length of 1024 elements. So we just assume that since we're never going to have more than 1024 elements for a stack, we could offset the insertion of an element in the stack of a specific context by a multiple of 1024. So for example, if you're working on the root context and you're pushing an element to the stack of length 1, then your new element will have the index 1. And if you're pushing an element to the stack of the second execution context that has ID 1, then you're going to push it to the first index offsetted by 1024 elements. So we push it to the dictionary index. So this is a solution that we have found to be pretty effective, even though it's still a bit more expensive than our initial design. But this is the logic that we have replicated to implement both the stack and the memory. And this is what we're going to keep building the Cairo one for now. So perhaps we can directly go and see the code of the stack and if it's on that code or in the
Yes, the cool thing here is that I personally don't know anything about Kakao's code base, so I probably have a bunch of questions that I'm discovering at the same time as I think a lot of people here. I was reading what you were saying about this problem with the destruct trait for self-referencing struct, I think. I was curious if you could show maybe an example of that, but I think if we go through the stack, it will be there.
So there's probably an open issue that shows it in the Cairo repository, but since we actually implemented the changes, I cannot show it now.
Okay.
But you can probably check and send links to the Cairo repository where I did a reproducible example. But yeah, so let's see that stack. How do I close everything? Okay. So first we have the stack trait, which declares every method available on that stack. And something that is pretty interesting here is that you can see that when we do stack operations, we do not return like basic types like U256. We actually wrap it inside the result type because that adds a layer of safety about how we can manage eventual errors happening in our code. So for example, the function pop removes an item off the stack, but what happens if the stack is empty? What should happen? Should we return nothing and do nothing? Should we panic, or should we handle the error more elegantly? So if we look at the definition of the pop function, you can see that if the length is 0, what we actually return is a result type, and the error we pass to it is the stack error. And so we have a module that is called errors, inside which we define every error. So all the EVM errors are defined inside an enum that associates the type of the error to an error message. So for example, if you take a look at the stack error, it takes a felt argument, and if we go back to the stack, we see that we emit an error with a stack and the flow error. So that's going to help us for debugging, and that's going to help us to manage the errors more effectively.
Yeah.
So
back to one small nice thing. Nice thing here that we didn't have before was anonymous. Empty enums, like empty values in enums, because before we had to we didn't have that. So in our code base, for instance, we had to put a value into it, and yeah, that could be annoying. But now I see that we have empty values, so that's definitely great and does help a lot. Is there any? That's an more open question, but do you guys think there is a future we would have some things like we have in Rust, like this error, being able to specify custom error messages, like basically be able to derive some standard error trait, which is kind of what you're doing here, but in the core lib itself. Maybe Shahar, if you have is that something?
Yeah, but like in Rust, for example, it started as a user library that was becoming polished and really good, and at some point they included it into the standard library. So we hope we get something similar here. So like if one of you wants to start this contender for a standard lib error, then go ahead. Okay, you're welcome. And I just had a small question about the stack trait. Did you think about using the generate trait attribute on this stack info, or did you purposely not use it?
So I think first, when like the stack was first written, the generate trait did not exist yet. And actually, I don't have a specific rule about whether I should use the generate trait attribute or not. But what I've noticed is that it makes navigating inside the code a bit harder, because since like when I'm going to use the stack in another file and I want to navigate back to the stack implementation, if I use the generate trait, I'm going to be redirected to a generated
generate file. Oh, yeah,
to a file. So what I actually like to do is, depending on, like, I don't have a specific rule, but I don't mind leaving explicit traits like this, because it makes inside the code base a bit easier.
But for example, for the machine and the execution context, we usually want to.
Yeah, like if you want to, like, if you go to the machine file, you can see here that we don't have a machine trait, and we use the generate trait here. By the way, like, I updated the code base to the 2.3 version of the compiler yesterday, and I found this very weird, unexpected bug, which is that if you don't have a white space between the comments and the generate trait macro, then it does not work well, and you cannot compile your code base anymore. Like, it took me quite a while to find that if I added back a space here, it would compile. So yeah, I found it more than that.
Great. Very weird.
Yeah. So back to the stack. Actually, here you can see something pretty cool. Is that when you create a new stack, we don't have to like define any specific behavior. We can just call the default trait to create a default stack, which is just an empty dict and a length implemented at 0. Because the stack struct derives the default trait.
That's
so
nice.
that allows us to, yeah, that's really nice. And that reduces the size and the amount of line codes that you need by a lot. And it's like,
I think we do that very well.
We do that pretty much everywhere. Like every single struct that we define in a custom way, we derive default on it or write our own implementation of it. And it's very handy when you write tests because it allows you to create like a default data structure very easily in your tests. And you can have specific behaviors. For example, if you want to test, you can go to the test stack here. So here we explicitly use the stack trait new. I think it's because when we wrote the test, we could not derive default already, but we could have used default to create the stack here and verify, for example, that a new stack 0.
Yeah, I think stack new is nice here. Like, otherwise, you'd have to call default with an explicit generic argument. Otherwise, you won't know what's stack. Yeah,
that's true. Okay, so yeah, back at the stack.
Small question I have on top of my mind. Just looking at the code, I see these inline always there. I think you already wrote some extensive GitHub discussion about this, and yeah, maybe you can talk quickly about the benefits and drawbacks and when should we inline the stuff. I think that does change with the compiler versions. Because there is, from top of my memory, there is some history of like right now we don't pay for the bytecode we deploy, and so it's better to put in memory. But that's going to change as far as I know. So it would be great to have your opinion, maybe Shahar, on this inline always macro.
Yeah, well, first of all, I hope that in the future, the inlining will happen automatically in the compiler. Like heuristically, it will decide when to inline and when to not. And then you won't have to do this manually. If you always use inline always, you might get exponentially sized code. I mean, that's not good for anybody if you have like a gigabyte of data for your program. Use it when necessary. Otherwise, like for all the trivial leaf functions, go ahead and use it. It makes sense.
And do you have like a rule of thumb on when to use inline and when not to use inline? So like, for example, here, the function that we see on the screen, set active segments, like the rule of thumb is we're just going to like modify one field of the struct, and having our function inlines avoids us to push every variable to memory before and when returning. So it's actually a lot less instructions of just doing this inline rather than executing the function.
Yes, that's a good point. I mean, when you pass parameters, like you can either pass them by using a box, and there you pay the price of boxing and unboxing. You can pass it by value, which might push all the values of the struct and copy it. And if you have like if this is expensive, you can use inline, and then it will be inline in the previous function, and no copying will be necessary. The function will just use the fields it needs from the caller, and that's it. Yeah. So if you have all kind of methods that just modify and don't call out of the things that, and don't have any recursion or loops, then yeah, go ahead and inline them.
Okay, great. So this is basically the rule we had for now. And you can see that actually all our methods defined on the stack are inlines because they have like very few instructions inside it. So we decided to inline them all. And after running some tests about gas usage, we found out that it actually was less expensive in gas, but we haven't checked the impact on the code size yet. Okay, so I can just give an example of a stack function. For example, the push method. So the first thing we need to do is get the length of the current stack. So as I said, this is not a data structure that simulates a single stack, it simulates multiple stacks. And if we check the len implementation, we track the length of every sub-stack inside a dictionary, and when we want to get the length of the stack we're working on, we just get that value from the dictionary. So when we're writing the push function, what we do is we get the length of the current stack. If it's gonna overflow, we throw an error. Otherwise, we compute the index at which we want to add our new value inside the dictionary that we use to simulate the stack. We insert our elements inside that index, and then we update the length of the stack that we're working on. And since we're storing U in 256, because the EVM uses a U256 stack machine, we have to wrap it inside a nullable pointer, a nullable type that simulates a pointer that can be or can be not defined. So that's why you have this nullable trait new, and we wrap the item inside it. All right, so next we can go to the memory. The memory, I think, reuses a lot of what you previously wrote for Cairo 0, if I'm not mistaken, or I don't know exactly who wrote it, but I think it was you. Like, for example, we can like the way the memory is implemented is very similar to the stack. So this idea of having multiple memories inside one single structure and having active segments that we're working on. And we track the length of each segment inside this bytes-len dictionary. So the memory is a data structure that contains 256 bytes words, so 256 bits, so 32 bytes words, but that is actually implemented as a dictionary of U128. So we have to, and that memory is byte addressable, so that you can actually store elements at specific offsets that are not cannot be divided by 32. So for example, when you store an element, you're going to want to store for the mstore opcode an element of size 256 bits. You can store it at any offset you want in the memory. And what happens is that we check whether that offset is aligned with our 16 bytes words, so 16 bytes word, yeah. So our U128 values inside the dictionary, and we get the index of the chunk. So like if our memory is implemented with multiple words of 128 bits, like this, word 0, word 1, word 2, when we insert a value of size 256 bits inside the memory, we first check whether that value is aligned with the words in our dictionary. So for example, if you store a U100-256 at offset 0, the chunk index is going to be 0. The offset inside the chunk is going to be 0 because you don't have that offset, and the offset you're writing into memory is divisible by 16. So it's a very straightforward way of storing an element, and we just call store U256, which is a custom method that, oh, this is what I was talking about earlier. Like I'm trying to see the definition of store U256, and it brings me to the generate trait result. So I can just access it like this. So we wrote our own extension of the FEL252 dict traits, so that we can actually store with one method called 256 view in the dictionary of U128. And what we do is just write part of the U256 in an index, and in the next index we write the low part. So back to the store function. This is the happy case where.
Does it work? think it's good.
Okay. Do we have sound, Danilo? Do you hear the sound? Let me check. Do you hear? Yeah. Okay. I confirm. We're back, and we're sorry for the small disconnection.
Yeah, sorry about that. My
we were
computer
talking
burnt
about-
in the sun. Sorry.
Yeah, so we were talking about how we would pack some elements, like U256 elements inside multiple U128 words. So I can share with you a diagram about how we
I had
actually do the packing.
a small question about that before. When do we have the DW opcode back? Because
Yeah.
right now this the power of choose is just very inefficient to do. We don't have the old good way of doing it basically in a constant complexity. So that, yeah. Okay, so you have the else if way. Okay.
Yeah, I have 127 branches of if else to have efficient computations of power of twos. But for now, it does the job, and it's more optimized than running like dynamic computations of power of two. And so we're just sticking with that.
Yeah, I think we are working on adding const arrays. I'm not sure what's the current status on that, but Gil is working on that. I hope we have it soon.
Okay, awesome. Good to know.
Yeah, I wanted to ask a question, if I may. You in both stack and memory, see you have this active segment thing, and you have set active segment, I assume. And I worry a bit about the unsafety of this. If someone down the line by accident calls set active segment and he forgets to restore this, then this might cause bugs. It's like this method is maybe too open. I was wondering maybe it's possible to redesign these structs to be some kind of maybe underlying memory that holds all the dicts and something like that, and maybe another struct that like memory view or segment view of this memory, that he owns this underlying memory. It has an active segment that cannot be changed, and when he wants to pass the control to someone else, then he can deconstruct himself and give the control of the underlying memory to another guy, and then grab it back after he's done, something like that. Yeah, I'm wondering if some kind of design like this is possible.
That surely would be possible. But the main reason we went with this design, it's because this was the minimal refactoring we had to do with the code base. So it's in probably 3 hours we can switch between this current design we have and the previous one where we had multiple execution contexts. And so what I was thinking about is, as long as this design allows us to work correctly on implementing the next opcodes and reach opcode compatibility and have an EOA account ready and everything with that, and if we need optimization and access controls and things like this, it can probably come in a second time. But the thing I'm afraid with that is that it makes the way of calling the memory methods perhaps a bit more complicated, which we would need to change the way of interacting with the memory and the stack in every opcode. So I haven't really thought about this yet. It's very new, but yeah.
Yeah, I understand what you're saying, but so maybe once you transition to Cairo altogether, so it will be easier to do these kinds of things. I was thinking that the change is maybe not that big. It's just instead of holding the dict itself, you hold this memory by value. And so, first of all, the interface to the memory stays the same. So every opcode uses exactly the same functions in the trait. And inside, instead of accessing directly the dict, you go through the global memory interface, something like that. But okay, that's for another time. Yeah.
That's a good idea. We'll think about it. Yeah.
Okay.
Okay. But yeah, as you can see here, this is the code of the machine, and basically only the machine, we cannot enforce visibility and who can access what yet, but the set active segment methods are only called inside the machine when we switch the current execution context being executed. But yeah, just to finish quick with the memory, basically what we do is a combination of div and div-rem operations and masks and shifting bytes to the right, and combining all the bits of our elements inside the relevant words, so that we can split our U256 inside 3 words and store that word in memory and have a byte addressable memory implemented using 128 bits words. Yeah, so this might be, if you're interested in seeing how this efficient memory is implemented, it might be worth looking through the entire source code.
Just out of memory, couldn't you use the new pack store trait to do that? Just in the more just implement the pack store trait.
The bytes array. Yeah, the bytes 31. You mean bytes 31, right?
Yes, I think so.
Yeah, I think that's the one you're talking about. So basically, I don't actually know. I haven't looked into it. This is probably worth exploring for optimization purposes, which is not yet the priority. So we're probably going to wait before migrating to another memory model. I'm not entirely sure whether it would be more expensive, less expensive. Yeah, but our mind is not completely made with this design. But for now it works, and it works well, so we're just going to continue implementing new features, leveraging this implementation. Okay, so perhaps a good thing would be to see how the entire execution flow of a transaction would work in Kakarot. So for now, we've been really focusing on implementing the EVM itself, so we don't have the externally facing contracts that you could call to execute the EVM bytecode on Kakarot. But basically what happens is that you have this execution file with the execute function, in which you create the new machine. So every time you're going to start execution transaction, you're going to create a new machine. And then we have this empty struct called interpreter that is just used to call the run function on this machine. And the run function is defined inside the interpreter trait. And basically what it does is it calls the decode and execute function, which retrieves the current program counter. And then we fetch the bytecode, and we execute the instruction at index of the program counter. So for example, here we fetch the instruction, the current opcode being executed. We increment the program counter, and then we call the different opcodes to apply. So for example, if we take a look at the exec add opcode, which is probably one of the simplest one, it's a very straightforward operation. Basically what happens is we take the 2 uppermost values in the stack, so at stack index 0 and stack index 1, we perform our overflowing addition of these 2 values, so that if it overflows a U156 values, it wraps back to 0, and then we push back this result in the stack. So actually, when you look, when you divide the EVM into every opcodes, most of them are very simple operations. This is just addition, multiplication, subtraction, division. You have some signed operations as well that are very straightforward. Then you have interactions with the stack, where you're going to push some values to the stack, or push values of certain sizes to the stack. You have some memory operations to interact with the memory, to load words from memory, store words inside memory, and things like this. And yeah, that's basically pretty similar for
if I can, I have two specific Cairo questions actually. The first one, I think I've seen the I-126 type. Yeah, from the, I think you implemented it yourself. Now it's in the core lib, right? If I'm not mistaken.
So actually, it's just a signed complement integer implementation. So if you look at the definition here, it's just a script that wraps a U256 value, but that is expressed as a signed complement representation. So if it starts with a 1, then you consider it's a negative value. And so I think the max value you can have is
just 1 dollar, I guess.
Yeah, I think that. Wait, which one is it? I don't have it by. I don't remember it exactly. Yeah,
and this is not the case from the type that's within the core.
It's not a. No, it's not the same, and it's not the same implementation. It's just a like integer encoded as two's complement. And so we use this actually because we have some opcodes like sdiv, which performs the sign division operation on two values of the stack. And so the way we implemented things is we have several methods that we can use to pop values of the stack, which is more elegant than popping UN256 inside an opcode and then transforming it into whatever value we need to use. So for example, if we pop a in 256, the only thing we do is just pop an item of the stack and then convert it with a into implementation, which allows us to transform a type T into a type S. And we actually have the same with a pop usize method that takes an item of the stack and tries to convert it into an item of size usize, which is 32 bytes. And also one thing, we have our own implementation of a trait that is called try into result, because the core library trait is called try into and takes a type T and outputs an option of type U. But for us, we wanted to work with results and not options, so that we could pass an EVM error type for the result. And a very elegant way of handling all these errors is to just add the question mark here, which, for example, if the pop method fails, that question mark here will return early with the error and propagate the error from the pop function to return from the pop usize function. And it makes the code so efficient and easy to read. Like basically with 2 lines, we replaced, I don't know, 10 lines of error handling and things like this and error propagating. So like it's a really nice pattern, and that's very, very useful.
Does it implement form too? The question mark?
Don't think question mark implements form.
Like in Rust,
technically, yeah, that's a good question. I know that in Rust, the question mark will automatically try to call the from trait. I don't know if it's the case in Cairo.
Yeah, I don't think it's yet, but it might be in the future.
Okay.
So one thing we haven't talked about yet is storage, because Cairo is not it's a sovereign blockchain. It's run on a Starknet stack blockchain. So the way we're going to implement storage is actually going to rely on the storage of the underlying blockchain. So there's also a small document that I can share that shows how we are going to implement the storage. So basically in Ethereum, you have the account state that is stored inside a database. And on chain, you have the hash of that storage that is stored on chain. But we started looking at how exactly Geth implemented that storage, and we realized that when Geth runs bytecode, for specifically the store and sload opcodes, it has a data structure called dirty storage that tracks every modification made to storage and only apply them at the end of the execution of the current context. And so we thought that was a smart design to do in Kakarot, because like the most expensive things you can do on StarkNet is write to a storage variable, because it's going to be committed to L1, and I think the cost is like something like 90% of the transaction is related to storage costs. So if we can limit as much as possible the state diff size that we're going to send on L1, we can save a lot of costs related to execution. So the previous design in Cairo 0, what we have now is that every contract account is a standalone contract, and when we want to write to storage, we call a method on that contract that is deployed on StarkNet, and we call write to storage or read from storage. And we wanted to go with this like slightly different design for the Cairo 1 migration, which is that we're going to leverage the fact that we can have all the storage inside the main Kakarot contract. That can be addressed by the address of the EVM contract deployed along with an index, so that we can like access the storage of a specific contract using its address. Sorry, do I have a diagram? I do have a diagram. It's a bit heavy. I'm not sure if it's easily readable on screen.
Yeah, it will be
what
hard
happens.
to read.
Yeah, it's a bit hard to read, but basically what we do is the key of the storage variable we're going to write to is the hash of the address of the contract, so the EVM address of the contract deployed, and the storage slot we want to write to. And we implemented a data structure that allows us to minimize the amount of storage writes we do. We call that data structure journal, so that if you modify multiple storage variables during a transaction, you're actually going to modify some kind of dirty storage or buffer storage that is just a dictionary that maps keys to values. And when you return from the execution context, you're going to finalize these storage modifications by actually writing them for real into storage. So let's say that you're doing a contract which writes, I don't know, 3 times to the same storage variable on L1. So for now, StarkNet does not optimize for this, and you pay the full cost of sending 3 storage changes, even though that might be modified in the future. But what happens is that we do some kind of caching and only send to L1 the latest storage update.
On StarkNet, if I'm not mistaken, within 1 block, you only pay for 1 storage change. But
yeah, that would be a thing. No, not between 1 block, but inside 1 transaction, you would only pay for 1 storage change, because you only finalize at the end of the transaction instead of writing to storage for real every time you do an sload or store opcode. Yeah, and so we can actually, it's very efficient. We haven't coded that yet, but the design is pretty clear. What would happen if for the store and sload opcodes? So this is pseudocode and it's not totally accurate yet, but you would get the storage address by doing a hash of the address and the storage slot. Then you would insert that inside the journal, and when you want to sload, either you get you have a value that is written inside the journal, and in which case you use that value and you read from that value. Otherwise, you just read it from the real storage using a syscall. And and when you return from an execution context, you just write, do a storage write syscall with all the keys from the journal, and that will write the value forever in storage.
I think this design can also help you with simulating EVM reverts, right?
Exactly. Yeah, because so we used to actually track storage changes so that we could revert the storage writes if the transaction reverted. No, if the context. If the context reverted, then we had to revert storage writes performed in that context, which was highly inefficient, because if you ever had a context reverting, then you would, instead of writing 0 times to storage, you would write twice for each value. And using this accumulator pattern is actually a lot more efficient than the other design. It's a lot easier, because when you revert from an execution context, then you actually did not write anything to storage, so you don't need to replace the previous values and spend a lot of gas to rewrite to storage.
Is this similar to Blockifier cache DB or not at all?
I do not know Blockifier at all. Maybe Matthias
does
knows.
It cache?
Maybe Sharp. There is a cache DB in Blockifier.
Yeah, it does have a caching layer, of course, but
is it the same?
I don't
The
hear
same
very
pattern or-
well. I think it's a simple cache.
Was asking whether that pattern was very similar to the one performed in Blockifier, where you have some kind of cached DB. Is that it?
Maybe I'm totally wrong. It was just like shots in black. I was wondering if Sharon, you were
Similar, yes. We do aggregate in a dictionary all the current changes, and on revert we just drop them. Otherwise, we apply them.
I think that's very similar to how Geth is implemented, this notion of during storage. Okay, so I think we can probably wrap it up very soon. Do you have like any questions, or Shahar, do we have any remarks or improvements, advice?
I was just curious about one small thing before that. So as you might know, there is this transient code that is coming, the T and T load. My gut would say that we have that naturally with Starknet. Like we don't need, you would not even need to add this, because it's like a natural property of building Kakarot on Starknet that you get this transient opcodes. But maybe if you have thought about that, I think we had a discussion.
adding one field in the machine, basically.
Okay, Elias is saying that it would just be adding one field inside the machine.
Yeah, because so I mean, I can open my machine.
Yeah.
We looked a bit at I need to close. Sorry, I needed to close the stream. Yeah, we looked a bit at transient storage. Transient storage, for context, is currently when you're inside the transaction, every subcall that you make. So, for example, I don't know, you're initiating a transaction, and then from within your transaction, you're checking ERC20, like USDC.balance_of. You're entering a subcontext, and so inside that subcontext, you don't have access to the memory of your parent and the stack of your parent. And transient memory is, instead of doing for each subcall separate and volatile memory, you have for the entire transaction memory. So it's saving a lot of gas for many use cases, just as swaps and so on. Because usually what they would do is store and then revert the store at the end of their transaction and then save some gas. But anyway, that's getting into a bit too deep. But yeah, for us, what we noticed with Clément is if we just add one field in the machine, and it's a transient memory, then everyone, like every single opcode, like every single subcontext has access to it. So then we just have to map it. Then we add two opcodes, T-star and T-load, and they just interact with this transient memory. So I think for us, it's one day of work.
And it's actually one of It's actually one of Kakarot's main strengths, is that when we have new things coming to the EVM, we can adapt very quickly our architecture, because like writing this new thing with Cairo is a lot easier than adapting a TK circuit to handle that. So it's very handy and very efficient to implement new features.
Yeah, and we definitely see that as a trend, with more and more people talking about EVM plus, just extending the EVM in many different ways. And having that in Cairo makes it even we looked at the code, we can see like how elegant it is. It's very easy to read, go through each opcode, and you guys did a very good job like documenting everything. To be honest, it's like very impressive. So definitely recommend, maybe like for anyone that wants to actually learn about the EVM. I feel like contributing to Kakarot is a very good way. I know that Clément is also trying to do one in TypeScript, but that's for another time.
Try to ask.
Maybe I can ask a question, but essentially my questions would be, we are implementing the EVM like in Cairo, so we have many ways of freedom, but we have also some limitations. So I wonder how is an opcode that produce RANDAO from the Ethereum consensus. For us, it has no meaning. So I have a weird time like adding a sentinel value or like a dump value. This is one example. Turn the current gas in your execution in your transaction. Also, gas price I don't know. We have but
it's not for Cairo, and